So I think everybody arrived. No need to ring the bell. Very disciplined people this week. Okay, I'll wait until tomorrow. Or maybe it was the great speaker we have at the 11 a.m. talk, and everybody wanted to be here on time. So this is the first talk of the second week, which means it's basically the first week of the regular program in this GGI workshop. So maybe worth explaining for those who've not been here before that we try to keep a light schedule with talks limited to 2 talks per day, not necessarily more than 6 or so talks over the week. Wednesday, in fact, we have a discussion that's going to probably be longer than 1 talk because some of you will present a small amount of slides, but multiplied by 3 makes a longer takes a longer time. The discussion is to involve everybody. The topic is about precision and precision for muon collider in particular. And that's why we start the program today with Kirill, who's probably, it's hard to find an area where he didn't contribute with precision calculations for colliders, so doesn't really need an introduction. But he has been very kind to agree to give us an overview on what are the limitations of this activity in producing precision predictions for colliders. And this afternoon we will have sort of a, I don't know if a continuation, counterpart, or any way Davide wants to introduce himself, because he will specialize almost on the same topic for electroweak, okay, electroweak matters. All right, so we have roughly a 1 hour target to end this talk, but it's not an hard target, especially because lunch is not going to be served anyway until 12:30. So no need to rush. Ask all your questions you want. I'm sure you are willing.
12:30?
No, there is no limit.
No.
In Rome, they used to say Russian style. You tell
lunch
me.
Is served at 1. Lunch is served at 1, not at 12:30.
Okay. Then even longer time. Okay. So as I said, we would like to have a discussion also during the talk. So if you don't mind, you may get more interruptions than usual. All right. So thank you again for agreeing to give this talk, Kirill.
Thank you.
Precision phenomenology is for colliders and limitation.
Yeah. So, well, thank you for giving me an opportunity to talk about this. And I would like to start by essentially saying 2 things. One is that I was not really, thinking about giving this talk until I think Wednesday last week when Roberta ambushed me with the request to give it. And so by my standards, one week of preparation is a little bit too short. So I apologize in advance for what you're going to see. And the second thing I want to say is that I don't work on future colliders. I mostly work on the LHC physics these days. And so a lot of my discussion is going to be somewhat vague. But you're going to see much more concrete discussion, much more concrete statements, hopefully in the talk by Davide this afternoon. So let me start by sort of defining what we mean when we say precision physics, at least on a theoretical side. So precision physics is supposed to be a relatively simple thing. You find an observable that you can measure with a high precision, and then this observable is supposed to be calculable with high precision as well. And then you do the measurement and the calculation, you compare the result. And if the result agrees, then you move on to the next observable. And if the result disagrees, and if the comparison disagrees, the 2 results disagree, and then you start thinking about what this actually means. Now, the goal of this game is to find simplest possible observables for which credible deviations can be found. Okay, I'm pretty sure that you all know plenty of different things where where we have seen 3 sigma deviations that eventually go away. So it is important to emphasize that the observables that we look at and discuss should be as simple as possible. And the ultimate value of this game stems from the fact that we believe that our theoretical predictions are based on the fundamental theory of nature. And for this reason, when we do these predictions in an ideal world, we don't have a lot of ambiguity. We don't have essentially a lot of knobs to tune. So what we actually do when we talk about precision physics, we sort of don't try to model physical phenomena, okay? We claim that we have a theory and we know how to derive unambiguous predictions and accurate predictions directly from it. So this also implies that if you find a deviation, then there should be far-reaching consequences of such observations. So basically, if we find an observable for which precision physics in this sense gives a disagreement between theory and experiment, then we should start questioning the fundamental theory instead of asking a question if there another mechanism, okay, within the theory that we for some reason failed to notice before that can give the same result. And I think this is very different from what we do. This is very different in comparison between what we do to what, for example, our colleagues in condensed matter physics do. When they find a deviation, they ask about a mechanism within the existing theory. They don't throw condensed matter under the bus, fundamental of condensed matter theory under the bus. And when we play this game, at least we pretend that the consequences of observing this deviation should be actually very, very severe. Okay. Now, when we talk about all this precision physics, we basically have to remember a few things that I try to list here. And the first thing it is important to keep in mind is that, of course, ideal worlds do not exist. And so this aspect of modeling creeps in one way or the other, almost for all things that we discuss. Now, it is important to remember that not observables are equal. There are observables for which theoretical predictions can be made in a relatively straightforward way. And there are other observables for which this is very, very complicated. And of course, the simpler observables should carry a much bigger weight in comparison with the standard, with the results of the experimental measurements. On the theoretical side, it is important to emphasize that we also want to use as simple tools as possible. So in this case, if we can do perturbative calculations, straight perturbative calculations in the context of quantum field theory, which we understand very, very well by now, it is a much better thing to do than, for example, to discuss precision physics where you have to rely on simulation tools such as Parton showers or even lattice QCD, okay? Because those things we don't understand that well. Then it is important to remember, and this will be essentially the important part of the important theme of the first part of my talk, is that standard model physics is not the same as perturbative standard model physics, okay? And even for seemingly perturbative quantities, at some point, if you keep increasing precision over and over, you will start feeling this lack of the lack of perturbativity, and this eventually poses an ultimate limit on the precision for things that we can study at colliders and elsewhere. Okay. Now I'm going to use this words non-perturbative effects, non-perturbative physics, etc., etc. And for me, this would mean that these are things that I cannot really control with great confidence. Okay, so when I say non-perturbative, this means bad. When I say perturbative, this means good. Okay, although the separation is not very clear sometimes. Because lattice has very complicated extrapolations to continue limit to zero, whatever, not zero, but small pi and mass, etc., etc. So if you talk, okay, we can have this discussion, a few slides down the road, okay. But I'm saying this. I'm not saying okay. Modern is probably not the right word, but it's a very complicated environment. It's a very complicated theoretical tool, and at least to me, it's very difficult to judge where certain statements are credible or not. And ultimately, this is what you're going to, have to do. Okay. All right. Yes, Michael.
In the projections for the future for HLLHC Higgs couplings, and actually for Higgs couplings in general, there's something called theory error, which is supposed to decrease by a factor of 2 when you go into the future. And theory error includes the effects in the last 3 bullets. So it includes both the perturbative calculation and the modeling of parton showers and other non-perturbative effects. And I think people need to understand this clearly in order to understand the credibility of those estimates.
Thank you. Okay, so let's take a look at an example. So let's take the z-width, which is supposed to be measured at future colliders with a very high precision, something like 0.02 MeV. Okay, it's a relative precision of 10 to the minus 5. And of course, as everybody knows, d decays to hadrons. It's a substantial, branching fraction. And hadrons cannot be described by quarks and gluons. Okay, but in a certain sense, we push forward with perturbative calculations using quarks and gluons, and try to use these calculations to estimate whether we can reach this 10 to the minus 5 on the theory side or not. And the question is, what is the mistake that we make by doing this? What is the mistake that we do if we use quarks and gluons in order to describe the z-widths with this precision? At which point does it fail? So the answer to this question is a little bit murky, but one can argue in the following way. So what we understand very well is not the decay of the Z boson, but actually what is called the correlator of two currents that you see here, okay? And particularly we understand this correlator very well in the Euclidean domain, meaning that the Q squared of this incoming momentum is actually negative. So in this domain, you can actually construct what is known as a Pareto product expansion, essentially considering a very large value of Q coming in, and then asking the question, what happens to this quarks or gluons that propagate in this loop in the sort of external chromomagnetic or chromoelectric field, okay? And this question was studied long ago. The answer to this question is known, and this is a sort of the expansion of this correlator in powers of Q over lambda QCD, in powers of lambda QCD over Q. So lambda QCD is the non-perturbative scale of QCD. Q is a very large number, okay, and eventually comparable to the mass of the Z. Now, this we have some idea about what this is. It's given by what is called gluon condensate and quark condensate. And the question is, can we use this information to say something about the Z-widths? Now, the relation of this quantity to the Z-widths, or here the cross-section for something to hadrons, is provided by dispersion relations that you see here. And now what I'm trying to do, I'm trying to sort of adjust the power corrections to these cross-sections in such a way that it gets something that you see here, okay? Now, if you do this, you can say that it is not inconsistent to expect that you have similar power corrections to this cross-section as ED cables, okay? Now, let's look at the numbers. So if I take lambda QCD to be 0.3 GeV and the mass of the Z to be 90 GeV, and I calculate this ratio and raise it to the power of 4, I get 10 to the minus 10. So this is a tiny number, okay? Much smaller than 10 to the minus 5, which is a good news. Now, an important reason we have such a strong suppression is basically the inclusive nature of this observable, gamma Z, okay? If you start putting additional constraints on the final states, then two things can happen. First, this power may decrease. So instead of 4, you can get 2 and maybe even 1. And the second thing that happens is that instead of mz, you will get sort of the transverse momentum of some jet or something like this that you get in the final state, which is typically smaller than mz. So there are two ways in which this ratio can decrease. And if it happens to decrease to the first power, okay, and we will see examples of this, then this ratio becomes 3 times 10 to the minus 3, okay? And 3 to the minus 3 is already not too far from something like 10 to the minus 5. And to give you an example of something where at least some level of this discussion should be carried, at least at some level, is, for example, the measurement of the forward-backward asymmetry for the big quark, which where you have relatively large perturbative effects that are reduced by taking echolinearity cuts. The echolinearity cuts are not very severe, but they are there. And so the question is by how much these non-perturbative effects affect what you see in those cases, okay? So I'm not saying that this is, what you should put here, for the gamma, for the width of the Z, but I'm saying that eventually if you get to these things, then we should face the fact that we don't have a theory of these corrections, a real theory, and this will provide an ultimate limitation for whatever we want to do for this or that observable. Now, what I want to do next is to actually consider a few examples of high precision studies at LHC and elsewhere, where these kind of effects can actually be seen, okay? And I'll start with the muon anomalous magnetic moment. So this is, if you want to choose a precision observable you want to work with, this is an ideal precision observable, okay? It is strongly dominated by QED effects, okay, that we understand very well. QED effects were calculated to 5 loops and 6 loops are estimated. It is sensitive to physics beyond the standard model at the level that we actually want an observable to be sensitive to, okay, at this point in time. And at the same time, in the past 20 years, there was back and forth between theorists and experimentalists trying to understand what exactly the measurement of the anomalous magnetic moment performed 20 years ago by Brookhaven and now confirmed by Fermilab actually implies, okay? So that's an interesting story. And I'm not going to go into all gory details of this story because what I want to show you is that there are limits to what we can do. And the first thing that I would like to start with is to show you 5 different contributions that you need to understand if you want to predict an anomalous magnetic moment at the required level of precision, which is about 100 times 10 to the minus 11, okay? So here is a gigantic QED contribution that, as I said, was calculated to 5 loop. There are electroweak corrections that look pretty innocent, you know, just exchange Z or W. There are hadronic vacuum polarization contributions that basically look like this, and this blob is supposed to tell you that hadrons are inside, so you cannot really do a perturbative calculation at this point. And then there is hadronic light by light that looks like this, and again, this H stands for hadron, so some, you know, complicated stuff is happening inside. Now, all these things were calculated, uncertainties estimated, and the deviation between the measurement and the result of the theoretical prediction was found to be around 200 times 10 to the minus 11, or 3 or 4 sigma, depending on how you do things. Now, just I think about a month ago, we were told that this deviation that was with us for about 20 years disappeared, okay? Not because the results of the measurement shifted, they stayed basically the same, but because theoretical predictions changed. Now, what has changed in the theoretical predictions? So the important thing that changed was the appearance of the lattice calculation, okay? By the BMW collaboration, actually, right here. And this result is not yet confirmed by any other lattice collaboration, okay? So basically, we are told, and I'm not questioning that this is a correct statement, I'm just saying, basically, we are told that there is a new lattice calculation, which is pretty complicated, which basically solves the problem, okay? Now, another interesting, you know, addition to this story is that there was a new measurement of the CMD3 collaboration. It measures a plus and minus cross section into hadrons in Novosibirsk, by the way. And they observed that in comparison to their previous measurement, the contribution of the raw meson, okay, to this cross section should be higher by about 3%, okay? And this, again, completely changes the story because as opposed, for example, to this number, you are now getting here. And it's a result of a 3% increase in a relatively, well, I don't know, complicated or simple quantity, hard to say. But 3% is not 200%, okay? So that's an important statement. When you play precision game, you're sensitive to these tiny effects, and this, unfortunately, matters, okay? So,
I mean, one of the funny things about the CMD result is that it's almost in tension with CMD2. It's how much faith do you put in the CMD3 result?
that's a problem. You see, I cannot possibly discuss 3% shifts in any direction unless I do it myself. I haven't done it myself, I don't know. I mean, how much you can trust the BMW result? You know, I look at their paper, I understand something, but not much, admittedly, okay? How am I supposed to decide whether this is the correct result or not? I wait for the confirmation, okay? There is, as of now, no second confirmation, complete confirmation, right? So what are we going to do? And again, you know, don't get me wrong. I'm not saying that anything of this is wrong. I'm just saying that with precision at that level, you put yourself into a situation where you have to believe what is being said, unless you do it yourself, okay? And this is an important, and the consequence of this is very severe, you know. Either you're going to believe that there is a deviation, or you're going to, you know, have to say there is none.
So now I'm forced to ask, white paper is because somebody sit in a room and agreed on
Sorry?
some white paper. White paper.
Yeah, white
is a-
paper, yes.
That to me reads as somebody sitting in a room and they agreed on something that looked reasonable that day. But
Well, I'll tell you something off the record, okay? Because I
Okay.
don't want to be recorded. But you should listen to this guy. This guy can make statements, you know, about white paper. But yeah. So now one can ask a question: what are the limitations of theoretical interpretation of the mu and G minus 2? Okay. I don't want to discuss lattice. Lattice lives by, you know, in its own world, so it's probably correct, but I have nothing to say about this. Then this dispersion analysis that uses a plus and minus 2 hadrons for G minus 2 is not a limitation per se, but it is definitely a substantial obstacle. I think that at the end of the day, even if you measure all hadronic channels at all possible energies with, you know, very high precision, and you have a good idea how to combine them, the real problem with this will be how to properly account for the photon radiation. Because hadrons plus photons, you know, doing consistently over different energy ranges is a complicated thing. And if you look at the pi plus, pi minus final state and meet a photon in the context of scalar quantum electrodynamics, then you're going to see a shift of about 40 times 10 to the minus 11. So any precision that is substantially lower than 40 times 10 to the minus 11, in my opinion, will be questionable. Okay, the current precision estimated in this from these measurements is about 40 times 10 to the 40 times 10 to the minus 11 indeed. Okay, then I want to point out this thing, which is not widely known. There are actually non-perturbative effects in good old electric corrections. Now remember, these corrections actually come from the exchange of the Z of the W. So these contributions look completely innocent. You know, you think, okay, I exchange the Z, I exchange a W, I exchange, you know, another one, and life is going to be great. But I'll show in the next slide that there are actually non-perturbative contributions in that. Now, precision of theoretical predictions for hadronic light by light, 100 times 10 to the minus 11 plus minus 20. In my opinion, it cannot be improved, okay? This plus minus 20, you can only improve it if you solve QCD non-perturbative. Now, again, there is a possibility that lattice will do the job, okay? This is a realistic possibility. I didn't believe in it, but now it seems that this actually might happen. Again, with all the limitations that, or reservations that one might have, you know, about lattice. So if you put all of this together, I think basically these non-perturbative effects for the muon anomalous magnetic moment contribute at the level of 10 to 20 times 10 to the minus 11. And this is a barrier which is impossible to pass by unless, again, you solve, you know, the physics of strong interactions kind of from first principles. Okay. Now, here is a short story about electric corrections. These are the one-loop things, okay? You can calculate them. It's difficult, but, you know, possible. The number is 140 times 10 to the minus 11. And then you say, this is a relatively large number. Maybe I want to calculate two-loop corrections. And then you calculate two-loop corrections. And then what happens is that you find diagrams like this, where you have two photons. So you have a photon in the magnetic field, and here is a Z. And because there is no interaction between three vector currents, you have to take an axial current here, okay? You take the axial current, and then this triangle becomes what is known as anomalous. And anomalous triangles must disappear, okay, in the ultraviolet, and if you take all the possible particles massless, so they're sort of sensitive to how you distribute the different masses in this triangle. You know, the fact that the up quark mass is not the same as electron mass starts, you know, being important. And of course, this also implies that these diagrams have a very strong sensitivity to infrared physics. That is again non-perturbative. So if you look at the current result for these anomalous triangles coming from the first generation, and if you look carefully, you will see that in this perturbative two-loop diagram, the result is expressed in terms of the mass of the pion, the mass of the rho, the mass of the A1 meson. And these things you don't see too often in perturbative calculations. So basically what happens here is that this, of course, is not a result of the, you know, perturbative calculation per se. There is a modeling aspect where you try to model the spectral density in this triangle using hadrons, and then you do the required integrals and you get, you know, a formula that looks like this. And of course, this formula cannot be, you know, considered as something that comes from first principles. At the best, this is an estimate. Now, numerically, this gives you a few times 10 to the minus 11. And again, if, and again, this in some sense gives you an idea of what is an absolute limit for things that you can do, even as far as the electroweak interactions go, okay? So the next thing I want to talk about is the top quark mass. That's an important parameter, and measurements at the LHC basically get you to a point of about 300 MeV, and 300 MeV coincidentally is comparable to the value of lambda QCD. And so one should ask whether one understands what this quantity means if you start measuring it with this precision, because the top quark is a quark, a strongly interacting particle. Now, there are two ways in which the top quark mass is determined at the LHC. One extracts it from total cross sections and kinematic and fits to kinematic distributions. And the simplest thing to understand in some sense is the total cross section, because for the total cross section, at least in the context of collinear factorization QCD, we can write a formula like this. Now, you can calculate the perturbative cross section for T-bar production. You know something about PDFs, so you can basically calculate this quantity in theory and compare it with the results of the measurement. Now, here, the question becomes whether or not there are what is known as these power corrections, lambda QCD over Q. And in case of the top quark, if there are linear corrections of this type, okay, and I'm not saying there are these linear corrections, I'm saying if they're there, then these corrections, these non-perturbative contributions that we have zero control over, okay, can actually change the value of the top quark mass that you measure, okay? And existing theory of these collisions, of hard hadron collisions, basically doesn't allow us to make any statements about these power corrections. And in some sense, without this, about linear power corrections, and in some sense, without this, is not possible to trust this ultra-high precision measurements of the top quark mass at the LHC. Now, the situation gets even more confusing if you look more carefully in this. For example, the top quark pole mass, what is theoretically called the top quark pole mass, is a poorly defined parameter in QCD and cannot be used for high precision discussion. The most precise measurements of the top quark mass at the LHC don't come from cross-section measurements. They come from fits to kinematic distributions, which are even more messy than the total cross-section. And there, it's simply impossible to exclude by any means the existence of these linear corrections, linear power non-perturbative corrections. And then there is an interesting effect that when people were constructing part-on-shallow Monte Carlo, they needed a lower infrared cutoff for the perturbative part of the radiation, and the dependence on this cutoff is logarithmic, but the logarithm cancels if you put together the model for the virtual corrections and take into account real emissions. The logarithm cancels, but the linear correction remains, okay? Because no one cared about linear corrections, when people were doing these fantastic things. And it was pointed out by Huang and collaborators that in a certain sense, these linear corrections in case of the heavy quarks fragmentation can destroy a balance between sort of perturbative and non-perturbative radiation that is tuned by looking at light quark jets. And if this happens, then this effect may look as a shift in the measured mass, and the dependence on the cutoff is this, okay? So there is a linear dependence on the cutoff, and this is called the Monte Carlo mass, okay? So Atlas tried to measure whether the Monte Carlo mass is real or not, and I think the result is, at this point, is somewhat inconclusive, okay? But it sort of shows you that, again, after some limit, even sort of technical things in certain, well-established programs start being important if you start doing high precision things. The next thing I want to talk about briefly is the strong coupling constant. I don't need to introduce it. Everybody knows what it is and what it is good for. And for a long time, there is a long-standing discrepancy in alpha S at MZ, the standard scale to talk about the strong coupling constant, where basically the measurement from inclusive quantities, for example, the Z widths, okay, is in disagreement with the measurement that you get by looking at so-called shape variables, thrust and C parameter at lab. Now, what is interesting about event shapes, okay, is that they actually receive significant contributions from 3 jets from final state with 3 jets. And when one does this fit, there is a standard assumption that the non-perturbative effects, or at least non-perturbative effects estimated, linear non-perturbative effects, lambda QCD over Q, are the same in the 3-jet and 2-jet region. Okay? Now, the question is this a reasonable assumption? So one can try and estimate 3-jet non-perturbative linear corrections in the 3-jet region with using the so-called renormal model. And if one does this, one indeed finds percent level shifts in alpha S. It actually helped to reconcile these results, although, well, maybe not completely, but at least they move the shape variables alpha S in the right direction. Now, although it is good to see something like this happening, okay, one has to really remember that this normal on business is a model. We don't have first principle theory to calculate these non-perturbative shifts. And so further, for example, perturbative improvements, calculation of high and higher order contributions to shape variables, in a certain sense is going to be completely pointless, because the first and the most important thing is to understand what to do with this non-perturbative things. Okay, so this is another very clear barrier in determining the value of alpha S from these shape variables with a precision that is substantially better than a few percent. Now, for hadron colliders, there is a separate story, which a separate set of issues that some people want to discuss. So I already showed you this formula, and we don't know anything about these power corrections. But even this formula without these power corrections, okay, the important statement that is hidden in this formula is the Spartan distribution functions are universal, right? And so you can measure them at, I don't know, at Hera, and then use at LHC, or vice versa. So the question is whether or not this is completely true, and there are doubts about this statement. And doubts sort of start appearing at 3 loops in QCD for processes with final state jets. Okay, now if this is really going to be confirmed at some level, I'm not sure how this can be confirmed or disproved. This N3 law predictions or description of jet processes, which is at the level of few percent accuracy, will be the ultimate limit on precision that can be obtained at hadron colliders. Okay. Of course, the underlying thing, part of the story here, and also for these studies at the lepton collider, is Spartan showers. And here again, there is an important set of questions: how to match this to fixed orders, how to quantify the uncertainties, and how to improve parametric in parametric sense hadronization models. So all these things become important. They're probably not limitations of principles, but certainly limitations of practice. This is a limitation of principle. We don't know the answer to this question, I think, at this point. Which one? There were so many.
Yes, there are many statements, and I feel that the theme is a bit strong, saying that we don't know anything about the about the power corrections. I mean, yes, it's a factorization formula for top quarks, for more exclusive observables, but for Drell-Yan, it's a theorem.
Yeah, I said processes with jets.
Yeah, right. And so it's not the biggest leap in the world to take something that we know, say those power corrections in Drell-Yan, and
we don't know power corrections in Drell-Yan.
I mean, this is Keith Alice and company. This is
no.
taking things out. The
factorization formula that you're talking about, stops here, I think. So this is what
there's a leading twist. We have a factorization theorem, right?
Yeah. So these things are up for a discussion. So I think the belief is that Drell-Yan n is equal to 2. Okay, but if you look at how this statement is obtained, there is something to be desired. But
yeah.
Sorry, can I ask a question about the diagram? Why is it that you have to have gluon exchangers on both sides to violate the factorization theorem?
I don't, Michael, I cannot answer this question. I draw the diagram just to make it beautiful. But I don't think you need to have them on both sides. Probably,
Okay, it seems like you could remove one gluon on the top and still have.
yeah, probably. Yeah. An important thing is that you have to have an interaction of this proton remnant with whatever comes out of the hard process. So that's the important thing. Okay. Okay, so now I want to talk about what I would call the perturbative challenge. So let's imagine that these non-perturbative things are somehow taken care of, or probably that they are not so important for physics of lepton colliders. And let's sort of just think about what we can do in the context of perturbation theory. Now, I want to start by saying, okay, that of course, if you look at what is expected to be measured at future colliders and what is the precision, what are the projections, I mean, it's mind blowing, okay, the precision. So there are a lot of things that one will have to learn on the perturbative side to match the expected precision. But I would like to say that currently we're actually seeing, in the context of the LHC physics, that sort of the depths of the perturbative expansion that we can achieve increases dramatically if there is a good motivation, okay? And I want to show you these two things. I don't know how many of you are familiar with this, but these are the so-called wish lists. They're put together by enthusiasts of perturbative calculations on the theory side and on the experimental side. Here is the enthusiast from the experimental side. And this is the list that we had 20 years ago, okay? And basically the one loop next to Linode calculations were requested, okay? And this is the list from 2022. And as you see, now they request the full loop corrections to Higgs production, 3 loop corrections to 2 jets, and there are also pretty substantial requests for TT bar production. So basically, I'm not going to discuss whether these are reasonable requests, if they're needed, if they're not, but I'm saying that if you compare what people thought is an important target 20 years ago, okay, and and you compare this with what people are requesting now, then clearly you can say that there was incredible theoretical progress over this in the period of these 20 years. We can do much more now than we were able to do back then. Okay. Now, perturbative calculations at high orders require 2 important things. One has to calculate loops, you basically see them here, and you have to account for the real emission. The real emission is important when you have massless particles, because if you start emitting like this, then these contributions are going to be infrared. There will be matching infrared divergent contribution in the loops. You have to put them together to get predictions for physical quantities. This is particularly important in the context of hadron colliders, but also for lepton colliders. This is an important issue because you can radiate photons. So I want to start with the loops, and instead of discussing what we can do, how we do these calculations, I basically want to show you 9 pictures, okay, one after the other, with the comments of what this actually means. And this should basically give you an idea about things that we can actually calculate now, okay? So we know how to calculate for-loop QCD corrections to decay processes, 1 to 2. So Z decays when all the particles inside are massless. So these are Z decays, Higgs decays, and so on and so forth, okay? So we can calculate them through optical theorem, taking the imaginary part of this 5-loop diagram. So this is not a science fiction, this is a reality. We can calculate what is different mass assignment. So you can take this mass to be, I don't know, the Z, and this mass to be the mass of the W. And people are playing with these things because they want to know the full loop corrections to a raw parameter. There is a 3-loop QCD prediction for 2-to-1 processes at hadron colliders. So processes where you produce a Higgs or a Z or a W or a pair of leptons. Okay, so these are the things that you have to calculate. Protons are colliding from this side, they're not shown. Okay, so this is also known we know how to calculate very well all the way down to a constant. There are 3-loop 4-point functions that have been calculated. They look like this. and not only Feynman integrals, but also amplitudes for massless particles. And in the context of LHC, they give you, 3-loop corrections to 2-photon production, the photon jet production, and the 2-jet production. Now, these are not complete results, it's only virtual corrections. We don't know how to do the remaining part of this, but the loop corrections have been done. Now, I don't know whether for future colliders, for example, to determine the luminosity, you need to have very high precision predictions for Drell-Yan, for Baber scattering. But for the Baber scattering, something like this would be a good starting point. If, of course, this is not sufficient because all these things are done for massless electrons, but if there is a way to go from massless calculations to a slightly massive calculation, then this eventually can give you a good way to at least start thinking about how to calculate the Baber scattering at 3 loops in QED, of course. There are 2-loop vertex diagrams where Z decays to quarks, and then there are electric corrections of this type. This is Z decays and Higgs decays. We know how to calculate these things as well. There are 3-loop corrections for 2-point functions with different mass assignments, and this can be interesting for calculating masses of W's and Z's and whatnot. Okay. There are 2 to 3 amplitudes and integrals and diagrams that have been calculated, and this is an important part of the story for example, 3-jet production or 3-photon production in the LHC. And from these processes, so for these calculations actually exist, the real one, the complete ones, where you go all the way down to cross-section. And these calculations were used, for example, by, I believe, CMS collaboration to measure the strong coupling constant at 1 TeV, okay, from a 3-jet to 2-jet rate. Again, so this is not a science fiction, this is a reality. We know how to deal with these kind of things where you have a 4-point function with one massive particle outside, and actually with massive particles outside can be both, and then massive particles inside. And this was done to calculate Higgs plus jet production, inclusive Higgs and di-Higgs at next to leading order in QCD. And finally, there are also 1-loop calculations that people keep doing. And this is an example of an octagon, okay, that some people compute in order to, calculate the background for 3 vector boson productions and proton collisions where you require the final state to have 2 jets, so these gentlemen, and then 3 charged leptons, okay? So all this is happening more or less now, okay? People do these calculations, and my goal in showing all this is to say that the complexity of perturbative calculations is not determined by the number of loops. There are much more that goes into what is actually difficult to do and what is less difficult to do, okay? So the complexity of perturbative calculations increases with the number of loops, obviously. It increases with the number of legs. If you add additional particles into a final state, it is more complicated than, to have less particles in the final state. It increases with the number of massive particles, both internal and external, although this is a slightly subtle statement, because what increases really is what I would call analytic complexity. You put different masses in, it is very difficult to express the result of the integration or calculation of Feynman diagram in terms of functions that we know. But at the same time, if you look at point 4, if you have more masses in diagrams, then typically you have less soft and collinear singularities, and this makes the calculation in some sense simpler. Not an analytic calculation, but perhaps a numerical calculation. And so in a certain sense, this point 3 and the point 4, they play against each other, okay? Now, the next thing I want to discuss is how we do these calculations, okay? And this is one slide that I try to summarize, how these calculations are actually done and what are the bottlenecks in this. So the first thing to realize, if you go to higher orders, at some point you're going to hit the fact that the number of Feynman diagrams you have to deal with is extremely high, okay? Now, I think it's still, we're still not quite there yet, although for things like 3-jet production, this actually has happened. And this gives enormous algebraic complexity You can overcome it using some computer algebra, etc., etc. But there are also more intelligent attempts to do something about this by trying to put together different Feynman diagrams and sort of simplifying the integrand before you start integrating it, okay? So this is very popular in the amplitude community. I don't think this sort of propagated down to people who do really, down-to-earth calculations. And I don't know whether this is really a promising approach, but people are using this, okay, for relatively complicated things, and trying to simplify the integrand, okay, or trying to simplify the starting point of the calculation. Now, once you have the starting point in some way, you sort of classify it in terms of Feynman diagrams, Feynman integrals. You put them into different families, and the family basically is a collection of propagators that you see here that sort of closes under the algebra of loop momentum and external momentum. Okay, and what you do next is you use this very simple identity, which is called integration by parts identity, where this v mu is an arbitrary vector. And the statement is that if you do the calculations in dimensional regularization that we always do these days, then this integral actually vanishes. Now, if you calculate this derivative explicitly and use the fact that you can every scalar product in terms of this Feynman propagator, then basically you get a set of linear relations for Feynman integrals, okay, with coefficients that depend on kinematic invariance and masses that you have in the process. So you create a huge number of these linear relations, okay, and then you ask a question, whether or not I can express more complicated integrals that contribute to this table of linear relations through the minimal set of integrals that are simpler by some measure. These simpler integrals are called master integrals. And this procedure of solving the huge systems of linear relations in terms of these master integrals is in principle extremely straightforward, okay? Because you basically can imagine doing this by Gauss elimination method, okay? In practice, what is happening is that this problem is of extreme algebraic complexity, in particular in a situation where you have a large number of kinematic invariants. Okay, you have large number of kinematic invariants, you have large number of masses, then all these coefficients, okay, that you go and constantly process when you express one integral in terms of the others, this process of simplifying these rational functions becomes extremely expensive. Okay, to the point that you actually cannot do this. All right, and so people are thinking about different ways to overcome this problem. And one of the something for simple-minded people is to say, okay, why don't we put numbers instead of symbols into this table? And there is a high-level version of this, which where people use what is called finite field arithmetics to sort of produce a huge amount of numerical data. Okay, by doing these reductions over and over and over again for different values of m's and s's and whatnot. And then from this huge amount of data, sort of reconstruct the rational functions that you actually need at the end. Okay, so this is again not a science fiction, it actually works. And it is implemented in codes and people use it. Okay, then from basically the same starting point, you can get a differential equation for the Feynman integrals. You take a derivative of Feynman integral with respect to a kinematic variable, energy, momentum transfer, whatnot, and you basically can show that you're going to get a linear differential equation, okay, where the same set of master integrals appears on the right-hand side. It's a vector, okay, and then there is some complicated matrix that depends on kinematic parameters and masses. And the question is, what can you do with this differential equation? Now, there are two sort of lines of thought. One is you have to simplify this equation, put it into the so-called epsilon form, where you have, this dimensional regularization parameter epsilon sitting in front of this, multiplying the right-hand side, and then try to solve it analytically. Okay, this works beautifully for relatively simple problems, and people who do this, they study special functions, for example, conjecture Foley logarithms, elliptic integrals that appear in certain cases when you do these calculations. The problem with this, or at least one of the problems with this, is that if you have many parameters, okay, and you even manage to solve this equation and you write the result in terms of these Goncharov-Polya logarithms and whatnot, then actually getting numbers out of the analytic result becomes a complicated problem, a time-consuming, complicated problem. Okay, so formally you have an analytic solution, but you cannot use it because at the end of the day you want numbers and not Goncharov-Polya logarithms. So you substitute numbers in, and then you wait and wait and wait and wait, and at some point it tells you, okay, the number is 1 or 2 or 3. Okay, so even this becomes a problem if you really start facing a complicated enough situation. Now, numerical solutions is a different way to go. So there is something which is called Dam flow. I'm not going to discuss it, but it basically, and there are simply ideas that you can take this equation and you can try to solve it numerically, setting boundary conditions at an appropriate point. An interesting thing about solving these equations, as we know it now, is that you can get unlimited precision basically, provided that you can wait long enough. Okay. There is another thing, another possible way to go is to basically just integrate, this master integrals, the Feynman master integrals numerically. This is what the program PySec does. It has a limited precision, okay, and is also time consuming. So this is sort of the the workflow. This is what people do when they try to calculate Feynman loop integrals these days. And you see that it is relatively well established. So now let me just summarize what I think this all means, okay, as far as the loop integrals go. So first I want to emphasize that we have very sophisticated, theoretical apparatus for these kind of calculations, okay. The past 20 years saw an incredible development in all possible directions, analytic, numerical, etc., etc. We are much better off currently than we were 20 years ago, okay. Now, another important point is that these things, I mean, it's LHC is still running, high luminosity LHC is coming, so people keep thinking about these things, and this development will continue. Now, whether these developments will solve all the problems on the perturbative side that you need for future colliders, I don't know, okay, obviously, but I think there are basically a few things to emphasize. One is that if you seriously look at electric corrections with large number of masses, I don't think there is any way to sort of think about analytic calculations. Okay, one has to go numerical. The question is when. Okay, now as I try to show in the previous slide, we do have some good ideas about how can we how these numerical calculations can be performed, and perhaps there will perhaps there are even better ideas that people will come up with. Now, reductions to master integrals is going to be a bottleneck. Okay, this is a very important part of the story, both because you reduce the number of integrals you have to calculate, and because you get differential equations from this. Okay, but an important simplifications for master integrals can come from for this reduction can come from the fact that if you're okay with using numerical values for the W mass, the Z mass, the Higgs mass, okay, this will help enormously, at least for precision electric observables, where you don't have a whole lot of kinematic dependencies. It is a little bit more problematic whether this will actually help if you start looking at complicated cross sections, okay, where you also have non-trivial dependence on kinematic variables. Now, calculation of master integrals in some sense can be performed using techniques we know. This was demonstrated for 2-to-2 processes for real at the LHC, and people are trying to do something similar for 2-to-3. So I think if you ask me, I think it's completely realistic that at some point you will have one number for, I don't know, the correction for an amplitude squared for a 2-to-3 process in electric theory. This is definitely possible in my opinion. What I think is going to be a problem is the combination of the need to sample the phase space for high multiplicity final state processes, okay, and the need to perform numerical calculations of loop integrals. Okay, both of these things are extremely time consuming. If you go for 2-to-3 processes, okay, the phase space is large. It's much larger than for 2-to-2. And so there will be one time-consuming thing on top of another time-consuming thing. And I think at this point, we don't have a good idea about how to overcome this problem. So if you ask me what is more difficult, okay, what is more scary, I would say that this is much more scary than this, okay? I can imagine investing 5 years of my life and getting the results for this, okay? But I'm not sure that even if I invest 5 years of my life, I'll be able to get the results for this. So this is more scary than this, okay? I'm not saying this is easy, but I'm saying from what we know, if I can extrapolate, this is probably simpler than, than this, okay? Now, I wanted to say something about real radiation as well, but I'll skip it because it's not so important. I'll just show you this. So, okay, I'll say maybe a few sentences. So there was also a very important progress at in LHC in theoretical developments in the context of LHC physics, where people understood how to do this real emission part of the perturbative calculations. So for now, we have more or less complete understanding of how to do next to leading order calculations for arbitrary processes, almost. And now people start thinking about how to extend this to N3 law, okay? Now, the question is whether these developments buy something for physics of next colliders. And I think that there is potential, but there is a useful information that one can get from this. So I think that one of the things which perhaps for these developments are useful for is that they might help to achieve high precision for general background processes at future colliders. They can help with improving understanding of electromagnetic initial state radiation at lepton colliders, also with resummation of logarithmically enhanced effects with high accuracy. And there is an interesting last point where if you go to muon collider or 100 TeV hadron collider, that Z's and W's actually become nearly as photons, but they carry mass. And the question is, are there possible ways to sort of simplify the calculations that one needs to do for the massive, gauge bosons, using the fact that there is a small parameter, the mass of the W divided by the square root of energy on the, transverse momentum or momentum transfer and whatnot. Okay, I don't think we have a complete understanding of how to do this. Okay, because we never tried. I mean, the mass of the Z was never a small parameter. It is becoming a small parameter now. So there is, again, a good motivation to try and understand it a little bit better. And this is my summary, okay? I will not, keep you any longer. I just want to say that indeed, I think the absolute limit on what we can do in precision physics and colliders and elsewhere comes from understanding of non-perturbative effects. And in some sense, the future high-energy lepton colliders, at least in as much as electric precision observables go, they're free of this problem for inclusive quantities. But if you start looking more carefully, then maybe you have to pay a little bit more attention to this, because at a certain level, if you start putting cuts on the final state processes, this non-perturbative effects, enhanced non-perturbative effects, may come back. Now, virtual corrections to processes at future colliders will have to be computed numerically. This can be done with high precision, there's no question about that, but it will cost CPU time, okay? So, as I said, the biggest challenge in my opinion, as far as this loop go, is the need to perform numerically, sophisticated loop integrals, calculate numerically sophisticated loop integrals, and at the same time sample the phase space. These two things at the same time, is a difficult problem to solve. And the last thing that I was trying to say, but very briefly, is that we learned a lot about how to treat real radiation also in the singular regions at the LHC, and hopefully there are some things that can be transferred to do physics at future lepton colliders, and definitely at future hadron colliders. So this is everything I want to say. Thank you very much for your attention.
First of all, thank you, Kirill, because you clearly made a big overview, and I think there is a lot to discuss. I see 3 or 4 already.
Okay. So thank you very much. I had 2 questions. One about whether alpha strong could be determined on the lattice one day. And okay, then well, maybe the question is we don't know. And the other question was about the ultimate precision that you foresee for the prediction of the threshold scan for the top mass determination, because there is some idea that this could be around, if I remember right, like 40 MeV? 50. And so if
50.
Theory, I'm worried about theory uncertainty on the prediction of the threshold scan. 50? No, I want exactly to know your assessment of the ultimate sensitivity, because if that is the theoretical floor, it also limits the useful luminosity that, for example, a muon collider.
So, okay, so lattice alpha S, I think eventually, I mean, there are results right now, right? I mean, so the question is, do you believe that the most precise, measurement of alpha S comes from the lattice or not? Well, I don't know, okay? I have no opinion on that. I think it does, but, you have to ask more, knowledgeable person. The threshold scan, I think that the theory is solid. One can probably believe 50 MeV. I mean, the results, the TT bar excitation curve was calculated to, about to next to lead in order. It's a highly non-trivial result. Again, the question is, I was trying to think about it, and I think I forgot. Maybe Michael knows this, but there were estimates of non-perturbative effects at the threshold. I mean, certainly for bound states of the top quark, you can say that there are some things that shift the levels, etc., etc. I'm not sure that there are similar things for the excitation curve, but what can help is the fact that this is a small system. Okay, so there will be additional suppression as compared to some other bad things that can happen. So there should be lambda QCD over the mass of the top raised to a relatively high power. Whether this has been done carefully, I don't know. The other question, of course, is whether you can. I mean, how much? But this is not a question to me. It's do you know the energy of the collision? How accurately can you determine the position of the peak and all these kind of things? But people are working on this. So.
So I'd just like to make a couple comments on this set of questions. The first one is that today, alpha S is known. I guess the best estimates come from lattice, and the answer is that it's about a 1% accuracy.
1%, yeah.
For the European strategy, there are various sheets that would approach 10 to the -3 accuracy. The one which seems the most powerful is to measure the Z width with the huge statistics of FCCEE. But the problem for that is that if you want to use precision electroweak to estimate higher mass corrections in standard model effective theory, you can't use that value of alpha S because it's got to be an input. It can't be
It's a circular problem, yeah.
So you eliminate that source, then if you get to 10 to the -3, that is a 10 to the -5, or actually 5 times 10 to the -5 error in the width of the Z, and it's actually the dominant, quote, theoretical error. So one should really worry about that. The other comment I'd like to make is about the top threshold. So there, the current calculation is, as you said, order n cubed LO. So the real question, I guess, for the future is anyone really going to do the end of the 4th LO effective field theory calculation.
Well, Michael,
And
I
you
will
say-
retire by then, okay?
No, is that going to prove the answer? And I think I guess my attitude is that this is, it kind of goes beyond the problems that you talked about in the calculation of Feynman diagrams. This is an extremely sophisticated effective field theory calculation already at n cubed O. Frankly, beyond my understanding. And things you would like to get out of it, like the Higgs exchange, appear only at the n cubed LO level. So in order to really trust those, you have to go to one more order in perturbation theory.
Well, okay.
I
I
don't
mean,
know.
this I'm not so sure about, okay? I mean, it's sort of factorized, right?
20 years, maybe someone will have the nerve to do that, but it's really daunting. This also affects other quantities that are relevant for the top threshold. So one of the quantities which is an input to top precision phenomenology is the value of the TT bar cross section at the top of FCCEE, which is 368. So that's currently limited to 1% accuracy by the same calculation, because it's so close to threshold that you have to take these threshold contributions. And if that can be improved, you could go to higher order, but it depends on the same bottleneck. So, you know, the answer is really complicated, and it depends on what people really will be able to do 20 years from now, which is very hard to
Before I probably go to Jürgen, who may have something to add, I want to say two things. For the top mass, I think we are looking at experiments could do factor 10 better than what Andrea proposed for you discussed 40 MeV in principle. And this convergence is not fast at all. As you were trying to argue, there is so many things that go into the recipe. And I would also raise a flag that I'm not really sure we are able to communicate how difficult it is to, this factor of 10 in theory calculations with our experimental colleagues, because we always have discussions on half MV or whatever improvements on these things, and then the elephant in the room is never addressed. So we may end up, that's my opinion, at least with a very same situation as we have now in the LHC, that the data is infinitely precise compared to the theory we can predict for M-top at least. And I think Jürgen has more information on how to merge these things.
purely theoretical uncertainty on M-top for measuring the threshold is about 10 MeV. So there is something by doing the next order, but as you say, it's very difficult.
Yeah, I had a different question, but I mean, there is a whole breakdown of the uncertainties that is left at the top threshold. And the biggest chunk is, as Michael said, going from n cubed LO to n4 LO for the non-relativistic part. But there are also like experimental selection efficiencies and so on. It's an optimization of the beam conditions. It's also the luminosity measurement at the threshold. Whether the experimental precision will be at the end between 5 and 10 MeV, we have to see. But this is roughly the ballpark. But I think that when we have this measurement, probably also on the theory side, we will be down to 25 MeV, something like this. The question I wanted to ask, so you mentioned numerical methods and you said, okay, this is basically only a question of the CPU power. But I mean, is there anything that you envision that this can be improved? For example, so what is your bet on usage of like quantum computing for these kind of things? Do you think on the timescale of the next 2 decades, this is unthinkable or?
Well, it's hard to make predictions, especially about the future. So I don't know, if this is going to be a solution, fine. People are trying to extrapolate amplitudes using machine learning methods into, places where things have not been calculated, but there is always a caveat, right? Because, okay, you can extrapolate if things are smooth, fine, if not. So I don't know. I mean, I hope something like this can be done. Also, algorithmically, okay, the problem is to do 2 integrations one after the other. Now, it can be that you can sort of do one integration at once and do the sampling both sort of in the loop space and in the phase space at the same time. Whether this is realistic or not, I don't know. But people are clever. So there will be some solutions, I suppose.
And this recent paper that was by Lance Dixon and Kyle Cranmer and company, where they tried to get these relations on multi-loop diagrams, where they tried to machine learn these coefficients that come up in these recursion relations. Do you think that is something that is generalizable to QCD, for example?
I don't know.
You don't know, okay.
I think that, people who have very concrete understanding of how, what the problems are in serious multi-loop reduction with large number of parameters, they looked at this problem. The best solution that was found is to actually use this sort of quasi-numerical methods, right? The rest, I have not seen anything that was checked on real, large-scale calculations. For the top threshold, by the way, there is another problem, which is the fact that top is unstable and decays. So then there is a question of, how the interaction happens between the top and the decay products and top, et cetera, et cetera. And these things are understood much less, significantly less than that's N3 log QCD calculation for quasi-stable tops. Of course, you need a width to be able to, go above and beyond the threshold, but there are things beyond that. And so one needs also electric effects there and this, and this becomes very complicated at some level. So I don't know whether this precision, very high precision, is attainable for distributions that you're going to see, because you're not going to see tops. You're going to see, B's and W's and whatnot.
But you're referring now to the soft gluons, right? That are interfering with the intermediate stages and so on, and do this consistently. But I mean, at the moment, I don't think that this is yet the uncertainties where people worry about. I mean, I think that starts to become a problem when you want to go, let's say, below 10 MeV or something like this.
Maybe.
But maybe I'm underestimating. But okay, would be my.
So since you're giving a litany of things are affected by non-perturbative corrections and gave a number of nice examples. So the current kind of best fractional uncertainty at high PT at the LHC is the W mass. So do you believe there's kind of a floor there? I mean, like in terms of your estimates or for the theoretical uncertainty?
Well, W mass is an interesting question because, I was trying to think about this kind of things. And well, okay, okay. So if we want to discuss the W mass, we can discuss the W mass. So the problem with the W mass, okay, is that the measurement is so precise, okay, that you can say with, straight face that we don't have theoretical tools to make predictions for anything at that level, okay? Now, let's discuss the transverse lepton momentum distribution. We cannot predict it with the required precision, obvious, right? So we have N3 law calculations for inclusive things, and we know that they change the prediction by about 1%, okay? By about 1%, pure QCD. So, 1% on the W, if this translates into 1% on the W mass, that's, the end of the discussion, okay? So you have to do something which in some sense allows you to bypass the need to perform perturbative calculations. And as far as I understand, the only thing that exists that allows us to do this is essentially the Z-mass measurement in the same setting. So you take whatever you want, I don't know, Pythia or Herwig, you try to tune everything that you can tune to describe the Z production. You take into account the fact that, I don't know, there are different helicity structures and whatnot, and somehow you come up with the best possible prediction for the W production. Sort of, betting on the fact that QCD doesn't care whether you produce W or a Z. And so then the question becomes, what are the effects that distinguish between the W and the Z? Okay, and these are effects that one has to focus on. And these effects are mixed QCD electroweak corrections, okay, that people have calculated, but I don't think that this is incorporated into in the experimental analysis. And then another interesting thing is the fact that Parton distribution functions are different. So you produce, I don't know, a Z, you have CC bar, you produce a W, you don't have CC bar, okay? Now, we tend to think that these guys, C, B, whatever, even strange, that they're all massless when they come like this, okay? But they're not. So the question is, what is the impact of these initial quark masses on these things that you measure in the final state? The answer to this question that people know comes again from Parton shells. You take the mass, put it in, do something and see the result. Okay, I don't know numerical shifts, but I think it's also not very credible. Now, the question is, do you have a theory of, massive colliding quarks in the initial state? Okay, the answer is that the theory does not exist, because the moment you put masses in at next to lead node in QCD, you're going to have non-canceling singularities at higher twist level, okay? Maybe you don't care about higher twist, I don't know, for this particular problem. But this, I don't know. I'm not aware of anybody, carefully studying these things. So probably it's completely irrelevant, but it's sort of interesting. So.
On.
Okay. So I'd like to make one comment which might be interesting to some people in this room. The theory of the Higgs boson itself is right now a little underdeveloped with respect to the state of the art that you explained in perturbative QCD. So for example, for Higgs to BB bar, we have the pure QCD corrections to end of the fourth LO. But the electroweak corrections aren't even done to n squared LO, that is to the two loop level. And there are many examples of this where people just haven't thought it's worth doing for the purpose of LHC. Probably the most interesting one, though it's also rather challenging, is Higgs to W star, W star, W star, and ZZ star. So there's some very serious work by Dittmeyer and his group, maybe 10 years ago, which does the one loop calculation, but I don't think anybody's attempted the two loop calculation, which would be needed for Higgs factor one Higgs factory results. So people who are interested in this precision calculation should look into this and maybe repair some of these holes that can be done with current technology.
So let me respond to this Michael's comment by going back here. I think that, something like this for the purposes of, future colliders would be actually very helpful. As you can imagine, not everybody, pays attention to all kind of things. And at least my perception was that, two loop electroweak effects, pure electroweak effects, they're still pretty far away, okay? But if you are saying that this is something that is important to look at, this, of course, is a useful piece of information. And it would be nice to have it, sort of, systematically laid out. I think this will be very helpful.
Exactly for this two-loop calculation in the electroweak theory, do you just so does the argument that you said before that you just need more computing power, you can use the same techniques apply? I think you need some new developments, both for the things that Michael said, but also I don't know, thinking about dipole or reduction at the collider. If this is something that is science fiction, or we know what is the path and we need more computing power.
Well, I'm not saying more computing power. I'm saying more computing power, but you see, I think a big question is, so this is a no. This is a relatively robust workflow, okay? A relatively robust sort of things. Now, the problem with electroweak is that you have a large number of parameters. If you treat these parameters as letters in your calculation, S, T, U, M squared, Y, M1 squared, M2 squared, M3 squared, you're going to die if you follow, this sort of line of this approach. The question is, at which point can you say that, your MZ is not MZ, but 91 GeV? And your MW is not MW, but, 80 GeV. If this can be said relatively early in the calculation, then you reduce the number of parameters. And if you have to do a reduction where only numbers appear, that's a much faster thing than, keep all these parameters in analytic form, because the main source of the time goes into simplifying very high degree polynomials that form a rational function that are eventually becoming the coefficients of this master integrals. So this is where time goes, okay? And this is complicated. Now, is this needed? Would you be happy to have, a result for a two-loop electroweak calculation where the mass of the Higgs is 125 and the mass of the W is 80, and the mass of the W with a star is a parameter? Okay? Is this okay? Or is this too restrictive? I don't know. But this will make a lot of difference.
Just to make sure, the issue is that if you were to do a fit to MW and Z, let's say, for electroweak fit or something, you want them to be parameters of the calculation. Whereas in other cases, you're just taking them as inputs. It's all about this kind of phenomenological issues, or there is an even further issue with doing calculations where you are not allowed at the beginning to use these values as real values because they need to be complex, or you need to keep it analytical dependence.
Complex is not a problem. You also can put complex numbers in, I suppose. But no, it's exactly this. Do you want to keep them as a parameter for future analysis? What changes if you take the mass of the W to be 80.1 and not 80? Or you're fine with at least the highest level perturbative calculations being done at fixed values? And is there a way to estimate in a simple way the shift that you can imagine? I mean, it will make a lot of difference for real, because numerical reductions, they are much cheaper than everything else. Now, then the other problem is that that numerically solving these kind of things, okay, is again for a large number of parameters is going to be challenging, because you will have singularities appear in the complex plane all over the place, and you will have to carefully go from, I don't know, infinity all the way down to where you want to be. So it's not a walk in the park, but we're talking about years from now as well. Okay, so
maybe I'm oversimplifying, because for my own business, sometimes I had to do this problem. Do you keep MW or you don't keep MW? And usually the solution is that you make several numerical values for MW, and then you interpolate and somehow with a good choice. Is it not worth it because you need to, it's not so fast, much faster? I don't see the problem really. You want to?
So another process that maybe we should talk about is E plus E minus to W plus W minus. So there, the one loop corrections have been known for 20 years. But there is a problem when you include the finite W width, because the W width is actually one order higher in alpha. And so you're putting together objects that are at different orders in perturbation field. And there are, I can't remember the exact reference, but someone interested shows me. there are different prescriptions for this, whether you're supposed to use the pole or other more phenomenological ways of including the W width, and they give different answers at the level of the precision of the one-loop calculation. So this problem has to be better understood to do.
At the level beyond, at the next order, or
No,
compatible with being an issue at that order?
so this has to be better understood to do the two-loop calculation.
Yeah, so the problem is that you have a resonant contribution and you have a non-resonant contribution, and you have to somehow interpolate. And when you interpolate, problems happen.
Right.
In the resonant contribution, you can resum certain things and left something outside, but once you move outside, this becomes more problematic.
So you would say naively, you look at the Feynman diagrams, you should put in a running width proportional to the S.
Which is not gauge invariant.
Totally the
Yeah, yeah.
because you don't get the right cancellation.
Yeah, yeah.
Gauge cancellation.
It's not gauge invariant. Yeah, yeah. Yes.
Can you say again why the n square vector boson fusion to you it's harder than that n to the fourth for the z into fermions? In the slide before this one, you stated something about vector boson fusion at n square being harder to compute. Maybe. Yeah, exactly.
Well,
so,
I have to calculate a loop. I have to integrate over this phase space.
So this is 5 legs and 2 loops. The other one, I mean, at least for FCC needs would probably be 3 or 4 loops.
See, the other one is, you know, 2 Z's and a gluon. Okay, so that's alpha electroweak, alpha S. So that's a pretty high order. But you see, for this thing, you have many diagrams, but you don't have this problem that you have a large number of kinematic invariants.
Mm-hmm.
So for this one, you can imagine that reduction, okay, at least with this, you know, developments in computing and whatnot, that the reduction actually can be done. Okay, and then because essentially this reduction will depend on the mass of the Z, okay, and then depends what you do with these things inside, but it's essentially a number that you're calculating, one number.
Fully inclusive.
Fully inclusive. Yeah.
Oh, okay. And
so, but this is supposed to, I mean, this measuring part is supposed to, you take this, you calculate this guy, you take the measuring part, you get what you want, roughly. So the number of parameters is small, and I think the number of parameters is an important thing. I mean, of course, you know, don't misinterpret me. This is a horrible thing to calculate, okay? But you know.
But how much, you know, of this would change because of, you know, acceptance cuts? Because at the end of the day, people want to compute RB, R mu, or
well, then you cannot do it like this, okay? Then you cannot do it like this. Then you have to do it as, you know, I don't know, a 3-loop vertex correction, a 2-loop vertex correction with an extra gluon, and this is a different game, okay? Because a 3-loop vertex correction, you know, is difficult. This is what we can do. Okay, you add another gluon, I don't know what will happen. So that's
I can tell you this is where the call it discussion, call it fights are happening right now. Can you do that? Can you not?
But you see, again, you know, I think that that the more, if you keep the number of loop fixed, so let's say 2, and you start increasing the number of final state particles, this rapidly gets out of hand. Okay, so that's a problem.
We will continue this over lunch, but if there are comments, apparently we have another half an hour before lunch, not according to the way I thought it was. So anybody, or I see already clapping hands.